Thank you all for attending. It's a great pleasure. I would like to welcome Vassilis again.
Thanks.
It's a great honor and privilege to have him. He will give us the second part of his masterclass in optimization in AI and dynamical systems. Without further ado, Vassilis.
Okay. So, in the first part for today's lecture, actually we're continuing with the second part of last time's lecture, which will conclude that unit in terms of an overview of what optimization is. And this is the last slide we had at that time, where I tried to create a classification, at least in terms of the relationship of the models to the types of data that we want to handle. So whether this data was in some way continuous decisions or integer, in some way quantities or binary or entire control functions, that indicated a different type of model formulation for what the underlying optimization problem being posed is, automatically almost from these variables, with some other twists, like in multi-objective optimization and so on. And then we had another stream of information that enters such a modeling enterprise of trying to classify the ingredients of an optimization model from, it is both mathematical as well as based on experience classification of models and submodels of categories. So, and then of course we have uncertainty, which is another source of model impacts in terms of our decision making, which then leads us to the next natural question is, okay, so we more or less know what we want to solve physically to achieve. We have understood how to write this mathematical model or algorithm, which is a simulation of my problem that I want to optimize and solve. Question is, how are you going to solve this? Can it be solved in real computational terms? And that's the next topic today. I don't know, did this go? Yes, this way. So that's what we're going to see, a short sample of important algorithms. So there are three types of algorithms associated with all applications shown thus far, and with others that I will show you later, that are related firstly with the solution of large linear programming and nonlinear programming optimization problems. Then the next level of complication from linearity to nonlinearity is to deal with decisions that part of them have to be quantized. They cannot be fractional. They have to be whole numbers. So you can have a mix of such decisions in the same model, which complicates things immensely by adding, obviously, what comes with integer decisions is combinatorial complexity into the model. And then over and on top of all these are questions of global optimality. And global optimality is something which cannot be overstated, but it arises because of non-convexity, which arises because of non-linearity. And so these three capture the essence of the hardest, I would say. It's not just the typical algorithms that I chose here, are the algorithms that are called to deal with the hardest aspects of quantitative decision making in the modern era. So for interior point methods, which is the first algorithm I wish to present here, has to deal with linear programming problems and their solution. Linear programming problems are convex in the sense that they can present to you a global solution based on linear constraints and bounds. The optimal point usually extremes at a vertex of the constraints, and there is usually a single global optimum. So that's a very important, in fact, the very first class of problems that was dealt with in optimization when it was first conceived of as a problem, as an area. So linear optimization is like this. So we have decision variables x, cost c, some linear constraints ai x, and some non-negativity bound say. So the first algorithm that made the breakthrough in this area was due to George Danzig, and it's the famous simplex algorithm, I think around 1948. It is a way, basically, the way this works, to find enumeratively the vertices by increasing directionality of either maximizing or minimizing your objective until there is probably no further point that will produce this minimum, and so you have the solution. This is how it works. So you start from here, then these are the vertices of your hyperpolitope, whatever, and you move in direction that is monotonically decreasing if you're minimizing your linear objective until you reach a point where there is no further feasible point around here because you're about to depart into infeasibility if you continue following the objective function. And that's the proven global solution for linear programming. And convex programming is similar. So the important thing, well, and this is a review from, I don't know how old this review is, but this was the work of 1947 on the simplex. And then the question was, okay, because linear programs can be enormous, because they tend to approximate sequentially nonlinear problems, or larger problems arise because of that approximation. So the question was, what is the actual complexity of solving such big things? The simplex at worst was shown to be combinatorial, so there's no proof. Statistically, by use, it shows to be kind of linear in the number of constraints or variables. But until '79, when first of all there was a theoretical breakthrough where Kakian, a Russian mathematician, showed the ellipsoid algorithm that showed that there could exist polynomial type algorithms, time algorithms for linear programming. It's just that the polynomial limit was banned. And then somebody came along in 84 1994 or something, Karmarkar, who showed the first interior point method for linear programming, working for AT&T, and so on. And then it was shown within a year or two, in '86, by some of the most famous optimization people at the time, around 1980s, somewhere there. It was Philip Gill, Murray, Saunders, Tomlin, Wright, Margaret Wright, and they showed basically that this rescaling interior point method people were thinking of was related to very early ideas in the 1950s using logarithmic penalties or barriers for your bounds, and increasingly making those bounds more tight to get in the limit a solution. And they showed that these two are equivalent, but equivalent to work originally published in the 60s. The barrier transformation is very simple. When you have a linear, let's say a constraint like this, which is greater than 0, then you can take it away from the optimization and add it to like an augmented penalty here, where mu is a positive small number, okay? And the logarithm balances the other way. That's why you have the minus here. Of course, you're not allowed to touch the value of 0. It's a hard bound. And this is equivalent to this, and in the limit, this is going to give you the solution to the original problem when in the limit you drive the sequence of mu to become effectively 0 plus. Okay, so tending down, okay, from one iteration to the next, and you arrive at the limit to the solution, and the proof is that the limit within within that tolerance is in polynomial time achievable, something that did not exist up until then, and this created what is called the interior point revolution. This is the interior point method, because if this is your interior here, where you're greater than 0 from the constraint, then you're only allowed to live here. You cannot touch, let alone cross over, because this is an infeasible evaluation for the logarithm. So that's what's called the interior point method, or the barrier method. This is a barrier, but the whole algorithm is called an interior point method because the solutions x always are inside from one iteration to the next. They may tend to touch it, but never really become exactly. So this is what people talk about, and of course, I mean, I won't insist too much. I'll show you an example, okay, where this was a linear programming problem with 4 constraints. So just to see that this is where you have mu as a very large value, which means you're asking the interior point method, well, ignore the objective, okay? Find me the most balanced point for your geometry of your constraints. And the most balanced point for this set of constraints, the polygon, is right here in the, it's called the analytic center. It's not the center of gravity. So then as you start decreasing your mu, you see that the minimizers are migrating more and more and gravitating towards what the objective is now pulling them, okay? It's saying the objective, you'll minimize me if you come more and more and more until the point you're about to not touch the feasible region, and then the algorithm has to stop. and accumulates the points to the vertex that is the corresponding solution of the original problem in the limit. And that's the interior point method, because all the iterates were inside the hard constraints. And it applies, and that was why it was a big revolution in these 80s, early 90s, this crossover of information from linear programming to convex nonlinear and then to nonlinear, because it inspired now a whole bunch of new, huge, enormous scale, we're talking millions of constraints and variables in nonlinear and non-convex optimization. Okay, you had to accept that you had a local minimum, but at least it was feasible, it satisfied nonlinear constraints, it satisfied your objective, and it was feasible. So this was opening up now the scope historically as an algorithm, the domain of very large, applicable, real-world, large-scale nonlinear optimization, which converged usually within. And nowadays we're easily talking about millions, like in nonlinear, and in terms of Newton iterations, in the order of 30, 80 maximum. So nonlinear programming, as I said, so this is the first impetus of algorithms, linear and nonlinear programming, the interior point kind of revolution of the late 80s, early 90s, which had also ripples through other domains where these tools were used in decision making, in management, what have you. So for convex problems, things can get even more extreme in talking about billions of variables, and that was probably late 1990s, early 2000s, for linear programming, or whatever that was. This was a portfolio risk minimization management problem they were solving. The mathematician is Gonzio in the University of Edinburgh. So, and that's old news. So, but the next application is not only optimization can be used as a planning tool offline, but nowadays optimization algorithms are running in a kind of model predictive mode, almost in real time, with real data, new data, and then you have the next updated best solution. And this is what I meant to say by model predictive control. Effectively, you have somewhere constructed, well, you have your process, whatever that is, your production facility, your company, a traffic system that you're monitoring between two endpoints in time or in space or both. So you call that your physical system, and then you have to have a computational analog, which will be, let's say, the digital twin system, the simulated subroutine, which has the same perceived inputs and outputs, but you can run it very fast, much faster than real time, so that you can use it to predict where the system would have gone with this kind of actions or controls. So you choose the best actions to bring your system within a controllable envelope. So you are creating a controller which is relying on you providing a good enough model for that purpose to control a physical twin system. So that is reliant on some algorithms that do two things. One is continuously run the most current model available for the process, but because processes drift, you have to keep every now and then readjusting the model you're using for the process. So if the model is a neural net or a machine learning model, a neural net, it means that the previous state of the neural net is no longer actually fitting well the current state of the actual process it's giving you values for, which means you have to refit the neural net every now and then. When you see a drift, prediction versus actual, you refit it. And then, of course, you use it within this controller. It is a controller, but it's a smart controller. It has a model, an adaptive model towards a given process, and it can be also be given economic criteria as well as safety constraints in its control envelope, what it's allowed to do. So those are what we call optimizing controllers. They're not just looking, oh, what's the most stable point, the quickest way to get there. No. Different trajectories have different costs, different trade-offs. This is where actually optimization can be brought into controlling a real process with a twin. So your twin is sitting here, it's being refitted when necessary, but overall it's being used in predicting the control that you want to implement now to bring the quickest possible some change in your system or restabilize it. Actually, a model predictive control system is how airlines are using MPC actually to as a repricing algorithm, depending on how many seats and which seats are available and how close you get to the departure time. So the variability of the price of the seats as you go and try to book later or whatever follows some kind of profit maximization MPC. So it's not just, well, I hate to say this, I'm an engineer, I'm making serious control problems. It's like also these invented problems. I'm sure people's jobs depend on this, but yeah, come on. Anyway, so I mean, and then I'm not going to go into this because this is really going to get deep, and it's deep enough as it is. This is a prelude to optimal control problems, okay? Because it means I can solve control actions with a preview to the future as to what impact these control actions will have. If I don't want to reuse this, and this is a one-off control, then I live with whatever my control is from 0 to 6, whatever time units. But if I want to roll it over and solve another optimal control, which makes it model predictive control, then, okay, you use this, implement it, step 1 forward, slide your horizon, predict the next steps, and go on and like this. And the reason why you're using a long receding horizon into the future is to stabilize or to even out, if you wish, to even out, average out very rapid transient high frequency events in your satisfying your constraints, so you just wipe that element out. So the next big bit now So these were the sources of very, very large scale up to now, not just possibilities. People were dying, they wanted to know how to do this. Suddenly they had these sparse interior point methods for nonlinear programming, and they could plug in millions of nonlinear constraints from discretizing model predictive control problems in finance, in various other areas where they do use them. Portfolio management is MPC. And in addition, it may also have non-linear constraints which are not convex, so it has local solutions. So the companies there in Wall Street would really be caring if you said, yes, this is the global, guaranteed. And then you may also have on top of this integers. So it's like there is an initial investment to open up a portfolio, a new portfolio section with some company. It's not like a continuous flux. So this brings on the complication of integer programming, which, to cut it short, it brings on combinatorial complexity and requires some specialized enumeration algorithms, implicit enumeration algorithms, to cut away part of the search space based on bounding. And how good your bounds are determines how much memory you're using before you throw away a part of the tree of the combinations. And obviously, the more variables you have, like this, the more levels the variables have, the higher the complexity. So I won't insist too much on this, in how it's solved, etc. I don't really want to do this. Not even this. Okay, this is how branch and bound work and guarantee the global solution of an integer problem. I don't want to do this as well. You'll have to take my words for this, and what I'd rather focus on is actually to convince you and remind you of areas that we all have seen in our respective quantitative fields in terms of decision-making related modeling with either 0, 1 or of a specific integer label value variable. So there are many things. I'll report some from my field, from engineering, which is process synthesis, and then some common areas with planning and decision making and OR in scheduling and transportation problems that all require integer variables. So in process synthesis, basically, you are trying to compose a plan, a flow sheet, or a new product, and you're saying, well, all the possible combinations and all the ingredients I can have are so many of this, so many of that, and they can be connected in these particular ways. Okay, the number is large, but I can include sufficient of each of those agents I want to include into my system design so that the optimal solution will tell me, well, you only need so many of these, too many, that you've given me. And always that will be the guaranteed solution. And that would be, in a way, a structurally also optimally designed problem which uses integer programming logic to get the solution. The overall model is a superstructure because in some way you've ensured you've included enough of everything to build you a skyscraper or a tiny little house. So if that's what your range of expectation is, and if you've included the materials to be combined in the model, that superstructure can and will answer your question in the optimal way. And this is something that a lot of people have used, both in chemical engineering, in product design. I think it's used in other areas where you just optimally choose just a tiny subset of ingredients you're allowing into whatever that product is you're designing. And this is a separation process plant. I won't insist on this at all. The scheduling is another area which is very important. And again, scheduling, in the previous example, you can associate with a piece of equipment a variable which is 0 or 1. Is this piece of equipment going to be purchased and included in my plan? Then the variable becomes 1. If not, it becomes 0. So in the same way, you can have a structure which allows you to decide the on-off switching of units or lines, production lines, for example, in a production facility or whatever refurbishment you are planning to do in some production or business enterprise which has flows. You, from time to time, want to do what you might call decisions that have to do with how my flows connect from one production step to the next. And in some cases, I may have to readjust this in real time, as they do in batch plants, in many different areas. So for example, wherever you have scheduling, airline scheduling is using integer programming, for example. Supply chain management is an area where this is heavily used. And also the scheduling of maintenance operations, where you have big units which their performance will decay with time, but you cannot just randomly say, okay, this is the dirtiest, this is the oldest, I will pick this first, because it depends on the size and what is supported upstream and downstream by the unit you are now attacking to restore. Because you might overload much smaller units and much greater later expense had you taken into your schedule into account a longer term horizon of those decisions in a model predictive way. And this is what we offered as a solution by combining with nonlinear optimization with my students. We started looking at these are refineries, heat exchanger networks. We're chemical engineers, what do you expect? So these heat exchangers are cooling down something and they're heating up something cold, so they're trying to minimize how much energy impact you have on raw utilities. You recycle energy. But if your boilers or heat exchangers get dirty, it means they won't be able to transfer the heat. Eventually you're going to start firing up the boilers and pay for that money. So you have to have some logic of deciding from period to period, say on a monthly basis, what am I going to restore from this collection of units, which is really critical now, in view also of the future, to minimize the average annual utility bills and environmental impact. And the reason why you want to do it this way is because there is also an associated cost with each maintenance action. you're going to send out an entire team potentially, take down a unit of your production for all week, and then put it back. Well, maybe not physically, but reconnect it back. Okay, so it could be any system that undergoes maintenance, not just engineering systems. But this is the picture I want you to take away, and the optimal schedule you get in this particular case, this is the unit number and this is the month in a 24-month period, I think, 2 years. So the black dots are the months over a span of 2 years that it decided that it predicts. You want to clean specific unit numbers versus specific months. And this is like the off season for that production unit because it will be critical to clean it down. So we compared this with Monte Carlo runs and various other ways, and it seems that what this is doing with a simulated fouling model for these units to get dirty basically over time, it showed that if you want to view this as the energy bill for your heaters to compensate for losing cleanliness on the surfaces, it evens it out over a long period of time, like a set point in a controller, the scheduler, which is indicating to you that you are actually doing something that has some physical interpretation and validity in terms of what this kind of maintenance scheduling is actually meaning. The optimizer is evening out over a long time the operating cost level. It's not allowing it to go up and down spiky. It just picks an average value and keeps it there. So that's not a random event, that the optimal solution is this. Now, other integer, so again, these are integers, okay, where we showed that you can combine it with very neat trick in reformulating it, so we can solve it as even in differential equation form, neural network form. We don't care what your model is, we say. We can do this multi-period thing over time, and guarantee you that we give you 0-1 solutions. Anyway, so another big area where you need 0-1 decisions is transportation. Transportation problems, the typical things that people mostly know is the traveling salesman problem or salesperson problem and the vehicle routing problem, which are related. The traveling salesman problem is like this. You have a list of some destinations, some cities, and the task is to start at any one of them and go to some others, but only visiting them once and then returning back to the original starting point. And this is, in the old days, this is how postmen used to collect the mail or the coins from telephone boxes in the street in the old days. So they would effectively have to solve a TSP because this minimizes the distance of the closed tour, and in some way, if the velocity is constant everywhere, then it minimizes time as well. So this is what most people doing that kind of job wanted, so that was the plan that they tried to follow so that they would do the job the quickest, to visit every destination, collect all they have to, and then go back. But this is delivery systems operate this way as well. So, I mean, it's a very old problem from the 50s with some silly prizes that they had at the time. And there is a website dedicated to the greatest advancements in the area. But a generalization of this is the vehicle routing, where you don't have just one dealer going around in a van. You have a fleet of vans and you want to dispatch them in subsets of your destinations and find out the breakage of your fleet and the subtours in some optimal way that satisfies now an enterprise objective function, profit, cost, whatever. And you get this kind of, what they call it is like a daisies, representing the tours of vehicle routing problem. You may also have, like in dairy products, you could have like time windows that each destination is expecting the delivery. You miss it, it's gone. Okay, so, and you may have capacities also for how much they can absorb at each station. It depends. But this is the generalization of this. They start like nice toy problems, but these are really, really hard, advanced algorithm design requiring applications to really get close to something that resembles a global solution. Forget this, okay? But again, these are integer decisions because you have a list of n destinations and an order of n possible visitation sequencings. So how you make this, correspondence between what's first, this city or the other city, and that is your combinatorial choice, which is done by 0-1 variables again, within linear programming and combinatorial optimization. Then a third big area of applications is something that I've been alluding to slowly, which is deterministic global optimization. The problem in general, when you have a non-linear optimization problem like this, some objective you're minimizing subject to equalities and inequalities and some bounds. This may have local solutions that locally, if you perturb in the Newton sense, you don't find an improving point locally, but in a small neighborhood. But that does not say anything about the global range, where usually, if a problem is not convex, it means it has a deeper point somewhere, which is the global solution. And this is the trouble with nonlinearity when it leads to non-convexity in the model. Because there is no known answer other than quantum computing. For continuous variables, not the standard one that people understand for combinatorial problems, the quantum annealing type would work in this. But as algorithms, there's no known answer to this combinatorial problem, which, in order to overcome it algorithmically, what we do is we are trying to find the global solution, the global minimum of the black line function. And what people do in order to find a deterministic envelope to guarantee within some distance where your global is, but that has that combinatorial cost that I'm saying, that's how you can do it, but that's what the cost is. You create some guaranteed underestimator of the total range of your objective. So anywhere you step, this is going to be convex, and it's going to have some unique solution somewhere. And it may have some derivative properties based on your original problem, like eigenvalues. Then what you do, you split your variable, if you only had one, you split it in the middle. This is still your original black function, but you split your variable domain in the middle, and you go sit in the middle, and you say, well, from left to right, I'm going to apply now two different underestimators, squashing at the point where I am sitting in the middle. So that means I create tighter, lower bounding envelopes by property of my cutting up my space in 2, so I have to deal with twice as many stored values, and each time you partition for each variable, this grows combinatorially. Okay, so, but anyway, this is the logic, and you say, well, one of these lower bounds is violating a previous upper bound. You get as upper bound 1 the actual value of the function here, upper bound 2 the actual function there, and you have these two lower bounds. But then you notice something, that the upper bound 2 here is less than the lower bound here. A lower, so it means X, this. It's proven, okay? You don't know where, you don't know how much exactly, but you know that of the 2 hats, you throw 1 away without having to examine any of these interior values. So this is implicitly, yes?
How do you find the underestimator? How can you make sure that you're underestimating?
There are ways to construct them artificially. For example, if you subtract the 2 bounds of a variable and multiply them, x minus x lower and x upper minus x, and multiply these 2 numbers together, you are getting a function that is a strong quadratic in x, in that particular x. And if your function is not convex, you can increase a weight factor in front of this quadratic function between the bounds, keep increasing it until you swamp the negative eigenvalue of your objective. Here. So you want an easy underestimator? Okay. So if you have this, which you want to minimize, but this is not convex, one way to start convexifying it is to add, let's say, xi minus xi lower times xi upper minus xi times some alpha parameter. I can make it alpha I, it doesn't matter. So this will be, so what I'm adding here is, or the other way, or a minus. I'm not sure which way, but this should be positive. What I'm adding here is a little function under each variable, like this, a quadratic, which I can make really steep if I want. So if my function is like this, what I'm adding to you here is an increasingly stronger and stronger quadratic as my alpha becomes larger and larger and larger. So this can start with something that just barely envelopes your function, and the way to do this is you can do an eigenvalue analysis on a function, or interval analysis, the eigenvalues of the Hessian, second derivatives of the function, and then accordingly you know by how much you have to tune the alpha up to have just the convex underestimator, the tightest. And so each time you cut your upper and lower, this becomes 1/4. So it squishes and squishes until it diminishes. That's one way. So, and then you decide which one to throw away. You throw away this, you reapply, and then basically you are partitioning your domain like this. So you cut and cut and cut, and you create a sequence of lower bounds and sequence of upper bounds, guaranteed at each iteration. So when they approach within some certificate tolerance, you have declared epsilon optimality certificate, the algorithm stops and says proven, global optimality proven, within this much tolerance. But it can say proven, okay, because this is a proof. The question is how many iterations? That's the big question, because these are polynomial algorithms. Sorry, they are combinatorial algorithms at worst. Areas of application of this are, for example, this is the golden chalice, in a way, of research in biopharmaceuticals or whatever, where you can have, if you solve the protein folding problem, which is a global optimization problem, non-linear and non-convex, then you could design golden bullet drugs for specific diseases or specific people to help them. But that is the big question. How do you go from this is a highly nonlinear, non-convex, combinatorial optimization problem, and yet it's so simple to write that an undergraduate will write it easily. The minimization problem is just the two-body interactions in the simplest form between a linear chain of amino acids. All you need is the parameters between the amino acids. You write this internal energy minimization model, and you realize it's extremely non-convex. And actually, this has an interesting property. The number of local minima is exponential to the number of amino acids. So anywhere you step, there's a minimum. Anywhere, everywhere. So a local solver is going to be like, oh, you gave me a minimum. What, the starting point? Yes. Statistically, it's exponential. That's why it's very challenging. So this is the end of this first part, which I hope to have spiced up a little bit things in terms of the most challenging algorithms. This is not stuff that normally people do like every day, even when they design algorithms. But these were how the applications gradually shaped libraries or classes of formulations of optimization problems or simulation problems that, if you look left and right at different disciplines, they're the same. It's just that people don't look left and right. They are the same. So basically, we are the model librarian keepers of similar applications where you realize, well, this is a wave equation, you're having a wave-like phenomenon, solve it that way. And that's how they got quantum mechanics, basically. So this is the importance of being able to be general enough in the decision making OR field, operations research, so that you can have an overview of models which allows you very quickly to tune to applications that could be business, translated in any way that we may wish within academic circuits, business. We all have a business, education, Well, generation of new stuff, new grant proposals, new ideas that go forward, papers, technologies that may allow you to approach new applications to generate real business there. Because suddenly you realize this application can be captured by a new formulation which has access to a new algorithm, which it didn't exist before here. There was an X. So these are opportunities, and this is how I think a model making group, a modeling group, a computational modeling group for, I would even say, futuristic applications, which involve hybrid, mechanistic, and machine learning technologies for the future. I think this kind of attitude should be centrally taught within an OR course and be part of the core of the activities, because that's your outreach. You can place yourself strategically as a group anytime, anywhere you want on this line or triangle, according to what your market response should be to the exterior as well as to the interior, what people you can attract. So by positioning appropriately each time across this, you have a strategy for a new outreach activity, I think, or a new, in my case, new research fund. So this is the end of the first.